All right, so we are working with, in this warm-up, scalar multiples. I added a grid on here just to make this a little bit easier for you to keep the same direction of your vector. You should also be measuring vector v just to see how long that is, and then kind of like doing your best to do a scalar multiple by 3, by a half, by -2, and by -1. So if you haven't done this yet, I'm going to take it up. But if you're watching the video right now, you can pause it before I start to take this up. Okay, so this is what you should get. It doesn't matter where you draw these. I decided to do 3v, and I doubled it down here and tripled it up here. It's a little bit difficult to fit kind of anywhere else unless it was like just above or just below. For 0.5, we should be looking at something that's about half the length of v. And then for -2v down in the purple, opposite length and double the length, opposite direction and double the length. And then -v should be exactly the same length, should be parallel, but opposite direction. Okay, so that's kind of what your vectors should have looked like. I did overlap 3v with v, so part of v is like part of 3v. Any questions for this one? Okay, so notice that I'm trying my best to keep these all like almost exactly parallel as best I can. Okay, when they're scalar multiples, they should be parallel. Okay, can I flip off this, or are we still looking at it? No answer. I will take that as I can flip off of it. Do you guys need it still? Okay. Okay. So today and tomorrow actually, we're going to do a few applications of vectors. So there's a few little things that we need for like setup information. So two vectors that are perpendicular to one another and add together to give vector v are called rectangular vector components of v. Oh, why is this not working? Uh-oh. Hey, what's up?
What's happening with the chapel today? What time is it?
11s and 12s are either at 10:15. I think we're at 10:15.
10:15?
Yeah, it's in B.
Is it block A over by then?
Yeah, it's in B for grade 11s and 12s and some 10.
So wait a minute. So, hold on a second.
Hold on, let me pause my video. See now too, so that's good. Okay, so they are called the rectangular vector components of V. Okay, sometimes they are called the perpendicular vector components as well. I just spelled that wrong. Very wrong. Okay, so I think I mostly use rectangular vector components, but if you happen to see in another text or whatever, perpendicular vector components, we're just separating out the vertical force and the horizontal force within like a certain vector. Okay, the other thing that we need to know is called an I always say this wrong. Equilibrant vector. There we go, got it. Equilibrant. And this essentially is just the word for the vector that kind of counteracts the forces of a combination of vectors. It is equal in magnitude but opposite in direction to the resultant vector. So if we happen to balance out the resultant vector with this, this red vector here that's labeled E for equilibrant, that means that those things are all summing up to give us 0. So if we have this in our system, that means that it holds our object at rest, okay? If I have two vectors, the resultant vector and the equilibrant vector counteracting, I get the zero vector. That means that the forces are equal and the object is at rest. Okay? Mark, yeah.
In this diagram, is like E the equilibrium
Yep.
acting to R?
And R is our resultant vector. So R is the resultant vector of these two forces. And the equilibrant vector is acting at in the opposite direction. Yep.
And where's our object? Is it in between the red and blue?
Well, in this case, these are just forces, but the resultant vector of the forces is being counteracted by the equilibrant vector. So in this case, I think like there's not necessarily an object, but we just consider those forces to be balanced. Okay? All right. So, in a numerical model of the Bay of Fundy, the velocity of the water is given using the rectangular vector components of 2.5 meters per second north 45 degrees west and 3.5 meters per second south 45 degrees west. Draw the resultant vector and, ladies with the conversation at the back, draw the resultant vector and find its magnitude and direction relative to the horizontal vector. Okay, so I always like to just stick some little X's or T's on some of these joints with my vectors. These help me understand kind of where these directions are. So I have one that is north 45 degrees west, which is this little vector or little angle measurement in here. And I also have my other vector. Oh, and this one we can label as it's already labeled, never mind. And this one we can show that south and toward the west is also 45 degrees. Okay, that leaves us with a vector, or with inside here being 45 and inside here being 45, and that's how we know that those are 90. We also kind of know that they're 90 because those are two kind of like, they're both 45s, so we can probably guess that the angle between them is going to be 90. Now when I draw my resultant vector here, we're going to use parallelogram method. I'll just make it a solid line. And parallelogram method helps us find the resultant when we have vectors arranged tail to tail. Okay, because I need the resultant to be the vector that results from arranging the vectors tip to tail if I'm talking about the resultant vector of these two forces. So this is my resultant vector. See if I can do that a little bit more straight. Not too bad. Okay, we're going to label this vector R. Okay, I know that the resultant, we might be like inclined to think that our resultant is facing exactly west because we have north 45 degrees west and south 45 degrees west, but we also need to take into consideration the fact that this is 2.5 meters per second and this one is 3.5 meters per second. If they were equal, then my resultant vector would be heading exactly west, but because these aren't equal, it's heading a little bit more toward the west than toward the south than it is toward the north. Okay? All right, so we need to figure out what this is, magnitude-wise and direction-wise. Zainab? So I always keep the forces going in the same direction as the original vector. So if this vector is going that way, I also make this vector go the same way, right? So I'm just keeping the direction of the forces the same.
And then why was the resultant going out?
So when we think about, you can either use like, it doesn't really matter which route you take, but when I think about going from here to here, I'm starting over here and then I'm ending over here. So my resultant vector should start there as well and end at the tip of the last vector. Okay? Okay. So I need to find the magnitude of this vector and I need to find the direction. If this guy in here is 90, let me just switch to red so you guys can see this a bit better. If this guy in here is 90, what do I know about this angle over here? Also 90, okay? Because these guys are parallel, I know that I have that C pattern in between there. Okay? We also know that this vector is kind of like the same as this vector below, so I'm going to label this. So we'll just use the triangle above. It doesn't matter, again, which one you choose, but I'm going to label that guy 3.5 meters per second. Okay. So I know two sides in a right angled triangle. Can I find the third?
Yes.
How? It's a right angled triangle. I know two sides. Pythagorean theorem should be perfect for us. Okay, so the resultant is actually the hypotenuse. It's across from the right angle in this triangle. So I should be saying that 3.5 squared plus 2.5 squared is equal to the magnitude of the resultant squared. Okay, I am going to square root this, and because we're already working in decimals, I think we can round here if necessary. What do we get?
3 meters per second.
Is that exact? 4.3?
4.30116.
Okay, I think that's pretty close to 4.3. So we'll say 4.3 meters per second. So why don't we just pencil that into our picture here? Okay, the last thing that I would like to know is, I mean, we can find either angle here. It doesn't really matter. But perhaps we can maybe find this angle inside here. Maybe I'll do it in green so we can see. Okay, I would like to find this angle inside here so that we can figure out maybe this little slice. Yep. Well, this one is 45 right here, but I also have this extra little slice down here, and I need to figure out what that total thing is. Yeah, I don't really know until I solve, right?
What if I like made a line so it like kind of touches it so like it looks like it's
Well, it doesn't really matter how you draw it, right? You still need to solve for it. But I already know that this isn't exactly 45 because these forces right here are different. If they were equal, then I could say this is exactly facing west, but because one of these is greater than the other, this is going to be slightly more south than it is north. They are, but one of them's longer than the other, right? One of them's pulling more than the other. Yes, exactly. So more south than it is north, right? Yes, it'll be more than 45 from this vector right here. Okay, so back to the task here. If I can solve for this angle right here, I should be able to get a good idea of where we are from the horizontal. Olivia?
Isn't it just 45?
Can somebody explain to me why this isn't 40? This is what I was just talking to Ryan about. Can somebody explain to me why this isn't 45? Mark, go ahead.
because like the two side like lengths that we have that were already drawn 3.5 meters
Oh,
per
the speed.
second.
Okay, got it.
Yeah, it's like
Yeah, yeah.
different. It stretches it out more so that
Yeah.
our blue line when we split it is more to the side.
Yes, thank you. Good? Okay. All right, so can I use the two sides that I already have, the opposite and the adjacent side, and just use SOHCAHTOA, because this is a right angled triangle, to find that angle in there? I'm going to do opposite over adjacent. So here, this is my opposite, and this is my adjacent.
We're finding the whole green, right? And, like,
Yeah.
blue lines.
Yeah. For right now, we are. Okay, and we'll do tan inverse.
54.46.
Lovely. Make sure you're in degree mode. 54.46, you say?
Yeah.
Okay. Yes, Mark?
Does it matter if we go like west whatever degrees south?
So this actually asks us for the direction of the vector relative to the horizontal vector. So we're actually just going to say, like, we're going to figure out the slice that's inside of here.
So like below the horizontal?
Yeah, and then we'll just say below the horizontal. So some of you guys talked about how this is 45. So if that little piece is 45 inside there, and I want to find this blue little slice inside here, all I need to do is take 54.46 and subtract 45 to get my direction below the horizontal. So we're going to do 54.46, subtract 45 degrees. What do we get? 5.46? 9.46. Okay, so can we make that 9.5?
Yeah.
Okay. Yeah, Mark?
Explain why we're subtracting 45 degrees.
So let me just erase here so you can see as I'm drawing. Oh, I can't erase anymore except for random things that I don't want to erase. All right. Guys, everybody look while I'm explaining this. Okay. If this right here is 45, I went north 45 degrees west. This red slice going from that line of my 2.5 meters north 45 degrees west vector to west is how much? If this is 45, what's the red slice? 45. Okay. My question asks me to state the direction of the vector relative to the horizontal. So I'm either going to say like above the horizontal or below the horizontal, that kind of idea. So I want this little slice right here that's below my horizontal. So if I know this, we just solve for this whole thing, this green theta here. So I know that that whole thing is 54.46, and I just want that extra little slice in there. Okay? Good? So we solved, when we solved for our theta, we solved for this whole slice.
How did we know that 45 was with the red?
So if I know that, looking at this part right here, I know that this is 90 and this is 45, so this extra piece must be 45 as well. Okay?
That's what I
Okay.
meant when I said the red thing was 45.
Okay, sorry. Okay, so I'm going to say that our resultant vector is 4.3 meters per second in the direction, or we'll say at an angle of 9.5 degrees below the horizontal. So if you want to say southwest, you need to subtract 9.5 from 90. So it'll be like 80.5. So it'll be south 80.5 west. But this one specifically asks for the direction relative to the horizontal vector. Okay? So this is the vector that we just found. We found like 9.5 below, like so. So far, so good? Okay. Yep.
How is it below the horizontal? I thought the 9.5 was like a blue sliver.
Yep.
Is that a bar?
So this is the horizontal right here,
Oh,
and then we're going below that.
okay.
Okay, we okay? Okay. Let me just pull up my other thing here. Okay, we are going to try this question here. Oops, too far. You guys want to go to groups, or do you want to try it at your own desk? Groups?
That sounds like a yes.
Desk? Okay, well, if you want to work in a group, you can feel free to use the boards here. So I want you guys to see if you can figure this out. We have sailboat's destination. They are traveling 8 kilometers east, and then from that point, 6 kilometers north. We're going to find the magnitude and direction in true bearing notation of the resultant. Okay? So I'll give you guys a couple seconds to get situated wherever you want to go. If you want to do it on the board, you can.
I remember.
Okay guys, so I'll just show you the solution to this. So the picture should be 8 kilometers east, and because we're going exactly east and then exactly north, we can consider those guys, oh, it'd help if I unfroze the screen for you. We can consider those to be meeting at a right angle. So we've got our 8 kilometers to the east, and then from that point we go up 6 kilometers. The resultant should be that red vector that I've labeled vector R. And because this is a right angle triangle, we can just use Pythagorean theorem, just like we did in the previous question, to solve for this. So when we do 8 squared plus 6 squared, and then square root it, we get the magnitude of the resultant vector. And then our job is just to solve for, I can actually solve for either one of these thetas, but if you notice what I did here, I actually just created a parallel line with that blue dotted line that I showed there, and then I can use a Z pattern to just decide, because I'm working with true bearing, I can find that little slice in there starting at the north line, going, we talked about how you have to go clockwise from the north line when we're working with true bearing. So I actually found this angle up here by doing the tan of 8, or tan inverse of 8 over 6. And I found this angle to be 53, which means that the one between the dotted blue line and the red vector here is also 53.1. So when we draw that, you could have also found the other angle and just subtracted it from 90. That works too. And then, so you should be stating that your resultant vector is 10 kilometers at a true bearing of, we need that 0 there for true bearing, 0, 53.1 degrees. Okay, and again, I'm measuring from when we do quadrant or true bearing, I am measuring from here this way. So from the north going clockwise. What's that, Mark? So I did tan inverse of this. Yeah. Okay? No, it's okay. Do you have another question? You're good? Okay. All right, let's hop back to our lesson here. All right, this one's a fun one.
Ooh, gravity. It's force of gravity.
Not exactly, because it's, well, it is hanging, but not moving. Okay, so we have a video projector, and this projector has a mass of 2 kilograms. It's hung by a 5-meter rope from the ceiling. The projector is, sorry, there should be a space there. The projector is pulled back 2 meters, measured horizontally by a horizontal force. The magnitude of the horizontal force and find the magnitude of the horizontal force and the tension in the rope. Solve using vector methods. So the first little note that we need to know for this question is that the state of equilibrium or no motion means the sum of all the forces is equal to the 0 vector. So for us to be holding that box, or the horizontal force to be pulling that box, the tension must be equal to the forces that are being exerted on that, the force of gravity and also the force, that horizontal force that's pulling that box, or the projector, I should say. So no movement means all the forces must equal 0. I'm sure some of you guys that have taken physics know this. Also, we know that the force of gravity can be calculated by doing the mass times 9.8. I know in physics you guys use 9.81. Yeah, well, in math we use 9.8. Okay. Shh. All you physics nerds, quiet. Okay, so let's draw a picture of what's happening here. We have a 5-meter rope, so let's just say this is like our ceiling here. We have a 5-meter rope, and it is holding our video projector. And then what happens from there is that we get this horizontal force that kind of pulls our, like we have to imagine if something's on a rope, it gets kind of pulled in like a circular motion, right? So it kind of gets like pulled up like so. But the horse is horizontal that we're pulling this box with. So the box gets pulled horizontally. The length of the rope is still going to be the same. The length of the rope remains as 5 meters, right? So my box gets pulled up there by some horizontal force. Okay, so do we really need like this part? Not really, because now the box is up here, right? But it is nice to, maybe I'll just draw that like in yellow. So this was the original position of our box. And then the box gets pulled up, like so. It is nice to have this little like 90-degree angle here, just when we're thinking about our forces. Okay, so I have some horizontal force. Oh, and we also know that this was pulled back 2 meters, measured horizontally. So we can label that as well. Okay, so all you physics nerds, talk to me about the forces that are on this box right now.
Gravity.
No, force of gravity.
Okay.
That's the only because it's not touching something, so it can't, actually no, it doesn't normal force.
Tension.
Okay,
X and Y tension.
tell me about tension.
It's not.
It has an X and Y direction. It's
Okay, so where would I put the force of tension here? And what direction is this going in?
Towards like the center of like where the rope is being like.
Very good. Okay, so my force of tension is actually this guy right here. In math, we just call this T. If you want, you can call it F with a little subscript of T. Olivia?
How do you know that's where the tension?
So the force of tension is actually counteracting the force of gravity, and there's also one more force on here. No?
Shouldn't tension also be the other
Kind of say that.
We have the horizontal force that the box is being like pulled by, right? So we must have some kind of horizontal force acting on our guy right there. So this is like the main force that our box is being kind of like pulled back with. So we'll just call that our force.
That's the horizontal force.
Okay, so the idea here, guys, is that if this box is at equilibrium, it's kind of like being held here, then the force at which we're pulling it this way, okay, we're pulling it away from its original starting point, as well as the force of gravity, should be counteracting the tension here, okay?
TX equals F. So who's making an equation? T is F.
Okay, well, let's just, before we get carried away here, why don't we find the force of gravity? Okay, the mass of our object is 2 kilograms. And we're going to multiply this by 9.81 meters per second squared. What do we get?
19.6. 2.
19.6 what?
No.
What?
19.6.
Units of measurement.
That's exact.
Yeah.
It's 19.6 exactly.
They're just doing that because it's 9.81. 19.6 units of measurement, people help me out. Newtons, there we go. Good.
Down. Yeah, down. Yes.
Okay, so one thing that we kind of have to understand here is that if I have a force of gravity, when I separate out this tension vector into its horizontal vector components and rectangular vector components here, these have to counteract the two forces that I have going on down here. So if my force of gravity is 19.6, the vertical part of that tension vector must also be 19.6 newtons. Okay, so I can call that 19.6. I know that the rectangular vector components are perpendicular to one another. So this is the tension in the y direction, right? That can be my tension in the part of that tension force. Okay, my other tension component of this is going to be the tension in the x direction, and that's going to counteract this force that's over here. So this force that's being pulled in the horizontal direction should actually be equal to the force of that tension vector in the x direction, right? Because we're at equilibrium, right? So all of these forces need to be kind of acting in the opposite direction to one another to keep this at rest. Okay, so could we find the So we have to find the magnitude of the horizontal force and the tension in the rope. Okay, so we have two sides. I have a length, and I have newtons. Yeah, Mark?
Would T actually, yeah,
You okay?
yeah, I saw it.
Okay. I know some information in this triangle over here, and I have the same units of measurement. I have a 5 meters, and I have a 2 meters. Could I potentially find one of these two angles in here to potentially help us out in this other triangle? I need some angles in here because right now I have 16 newtons and I have 5 meters. So that's kind of a problem in this left triangle that I've created, but in the right triangle that I have over here, I have a couple lengths. So at the very least, could we maybe find the direction of the tension vector? So could we just, yeah, go ahead. Yeah, so we'll use cos of theta, lovely. And that's going to be equal to our adjacent side over our hypotenuse, keeping in mind that I need to do this in this particular triangle because they're both in meters. I can't really do anything just yet with 19 newtons and 5 meters. That doesn't really work. So let's do the cos inverse. Okay, we'll round our angle to the nearest tenth, so nearest decimal place. Sorry, what'd you get, Mark?
66.42.
Okay, so can we just say maybe 66.4? Okay, that's this guy in here. That also means that because this is a horizontal length and this is a horizontal length, I can use the Z pattern. So just to show you in red quickly here, if I use this Z pattern, I know that this angle and this angle are equal. So I also know that this little angle inside here is also 66.4. And if we want, we can also find this angle in here as well. That would just be 90 minus 66.4. Olivia? You're okay? Okay. So what's our remaining angle inside that triangle? 24.6. Lovely.
23.6.
Oh, 23. Yes.
23.57.
Why is this not working? What the heck? Okay, there we go. 23. Okay, so this is good. We're getting somewhere. We have an angle. We have two angles in our right angle triangle. We have the y force. Can we find the tension and the horizontal force? Keeping in mind that the horizontal force is actually equal to this horizontal force here as well. So the tension in the x direction will be just the opposite direction to the tension in the horizontal direction. So can I find this tension vector and can I find its horizontal component? Can we find two sides of this triangle? Okay, so I should be able to, this is, let's say we use, I don't know, we'll use 66.4. It doesn't really matter which one we use. If I use 66.4 as my reference angle, this is adjacent, this is opposite, and this is hypotenuse right here. That's the tension vector. So let's start with the tension vector. So if I want to find the magnitude of tension, or actually, you know what, I'll just set up the trig ratio first before I get into all that. So 66.4, I have opposite, and I'm looking for hypotenuse right now. So we'll use sine. And this is going to be the opposite, the magnitude of the opposite vector, and it will be over the magnitude of that hypotenuse, which is our tension vector. Okay, so I'm just going to multiply this up and divide out the sine, which will tell me that my magnitude of my tension vector can be calculated by doing 19.6 newtons divided by the sine of 66.4. Okay, so about 21.4 newtons. Lovely. This doesn't ask me to find the direction, but if I wanted to, I could say that this is at a true bearing of 23.6 degrees.
So that's 21 Newton was the top line. Or the
This is the blue line right here,
okay.
just the full tension vector. Okay, and I also want to find the tension in the x direction. And if I find that, it should actually be exactly counteracting the force that's being pulled horizontally in the opposite direction. So, I mean, we can use Pythagorean theorem for this. We can apply another trig ratio. It's up to you guys, because we already have two sides of our triangle. So I think we could just use Pythagorean theorem and just say the magnitude of the tension in the x direction plus the magnitude, squared, of in the y direction should equal the hypotenuse squared. And I have two of these already, so I'm just going to do like 19.6 newtons squared, and then our 21.4 newtons squared, and then we'll isolate for the tension in the x direction. This is also equal to our horizontal force that we labeled in our diagram up there.
But isn't the tension the x equal to like the tension of like the force of choosing? Oh, do you not know the force?
Yeah, we don't know. That's what we're trying to find. So yes. Okay, so don't forget to square root.
Why
Yep.
don't we just find it like straight away? Like, couldn't we find
Like
like
using something to
We can, or we can use Pythagorean theorem. We can apply either. We still have to find one of them, right? Okay, so what do we get here? Yep, that's exactly right. Should get 8.6 newtons. So this is that horizontal force. It also happens to be the force of the tension in the horizontal direction because we're at equilibrium, right? So this force must balance out to equal our horizontal force up here of tension. Okay, so you should get 8.6, and the full tension force there is 21.4 newtons, just the magnitude. Questions? We feel okay about this? Cool. Yeah, you'll have to practice some of it. Yeah, it's different for sure. Okay. All right, a couple more applications. Today is going to be a little bit longer, just so you guys know, and then tomorrow will be shorter and you'll have more time to practice. Okay, so another application of vectors is like airspeed and current speed and stuff like that. So we have a plane. It is traveling north 40 degrees east at an airspeed of 100 kilometers per hour. The measurement on the ground, so we call this ground speed, indicates that the plane is traveling north 45 degrees east at a speed of 1050 kilometers per hour. What is the velocity of the wind? Okay, so why, let's just think this out for a second. Why would the plane be reading a certain direction and speed, and why would that appear different on the ground?
the air.
Yes. So the wind is blowing the plane in certain directions, and also either if it's traveling with the direction of the plane, it may be actually helping the speed of that plane, right? And pushing it, or it could be counteracting the speed of that plane, so maybe the speed of the plane is actually a little bit less than what the speed measurement is in the air. Okay, so the important thing to know here is the velocity of the airspeed, so, or maybe I should just say airspeed, the airspeed vector plus the wind speed, or wind velocity, is equal to that ground speed that we're talking about here. So far, so good? Okay, so we're going to draw a little picture here. So start with your quadrant grid. We have north 40 degrees east. If you would like, you can also try to create like a good scale for this as well. So maybe you say that, I don't know, 5 centimeters is equal to 1,000 kilometers per hour, something like that. I'm just going to do my best on here. Okay, so this is going to be 40 degrees inside here, and I know that this is 100 kilometers per hour. And this is the velocity of our airspeed, so we're going to call this velocity air. Okay? And then I have another vector, which will be actually the resultant vector, which is the velocity that's observed from the ground. And that's saying that I'm about 5 degrees over and just a little bit further, a little bit longer. So velocity ground is 1050. And I know that this little slice in here is actually 5 degrees. Okay, so the velocity of the wind, I don't know if it's going exactly in like an east or a west direction. I'm not 100% sure. So I do need to find some information about it. So I wouldn't necessarily like draw it going like due east or whatever. But we know it's something like this. It's going kind of like, it's pushing us further into the east direction. So we know it's kind of like something like that. Okay, so notice here, guys, because of this idea, like if the ground velocity is actually your resultant vector, I need my air and my wind to be arranged tip to tail. Okay, so that's how I knew that the wind was going in this direction, because I want to arrange that that airspeed and the wind speed in the as like tip to tail, and the ground velocity should be the one that connects to both of those. Should look like the resultant vector. Okay, so my red vector is actually the resultant vector of the air vector and the wind vector, or the airspeed vector and the wind vector.
You said, how did you get from here?
Because I need my red vector to actually be the resultant vector of these two vectors right here. So if this is my, yeah, you got it? Okay. So the air vector and the wind vector, or I should say the airspeed vector and the wind vector, should be arranged tip to tail. That's the idea.
Why can't we keep them this orientation?
Pardon?
Why can't we keep them like, keep them tail to tail?
You can, but I'm just saying I knew that the direction of this had to be over here because my velocity has to be the resultant vector of the addition of the airspeed vector and the wind vector. So notice how my airspeed vector and my wind vector are arranged tip to tail, and then the velocity vector for the ground is actually the resultant vector of those two things. Okay? So we actually are going to use cosine law because we have two sides and one included angle or contained angle. And this will give us the magnitude of the wind. So that should be 1,000 squared plus 1050 squared minus 2 times 1,000 times 1050 times the contained angle, which is 5. And remember to do the square root of this once you've calculated.
102.26.
102.426, you said? Okay, so make sure you can get that in your calculator. I'll give you guys just a second to get caught up here. Okay, because I'm asking for the velocity of the wind, when I say velocity, I want the speed, which we just found, but also the direction of the wind. So we just found the speed. Our job is to find the direction. We can use, if we start with quadrant bearing, a lot of times we'll answer in quadrant bearing. So sometimes I just like to kind of put in some quadrant things here just so we can think about like Z patterns and things like that. So the first thing, like we can find this whole thing for sure, but I also just need to be mindful about like what vectors are equal and where they are equal. So I don't know, just I know that like this is 45 right here because that's 40 and 5, so that remaining vector must be 45. I know that this vector, so if I outline this right here, this and this are parallel, so the vector that's between there must actually be equal to What? Not 45. What's this vector?
Oh,
50. So this is actually 50 degrees over here. Which means that this little slice in here is what? 40.
Oh, okay, that little green thing, okay.
Yep. Because those are at a right angle, right? This thing right here, just so you guys can see a little bit better, that's 90 degrees. Just between the south and west line. Okay, that should actually help us a lot, because if I can now find this whole angle measurement inside here, and I know that that's 40, I should be able to find any remaining little pieces that I want to find. Mark?
I don't understand the top.
50?
Yeah.
So do you see this blue Z pattern that I've shown right here? So this must be equal to this interior guy here, okay? Yeah. So this, when we do questions like this, there's actually a lot of this. So finding like those Z patterns and understanding like that each quadrant adds up to 90 and stuff like that. Okay, so guys, I'm gonna find this whole angle inside here now. I wanna find that slice right there. So we're gonna use, we can apply sine law, cosine law. I think sine law is probably like our best bet here. So we're gonna call the whole thing angle theta. So that's the measurement of this entire slice here. I know that this little piece is 40, but I wanna know what the rest of that is. So sine of theta over its opposite side, which is 1050, should equal, and I think we have only one other side and angle pairing, which is 5 degrees over 102.4. So we're gonna multiply up the 1050 and do the sine inverse. Okay. Brian?
Yeah, I just don't see where you're getting all these numbers. I see we got the 50 and 40, but I don't see where you got this.
So I'm using sine law. So here's our triangle right now. If you just want to, sometimes it helps just to redraw it just with what you know. So we know 5 degrees, we know 1,000, we know 1050. I'm looking for this. I'm looking for that whole thing right there. And we also just found that this is 102.4. So I'm using sine and its opposite angle. That's where I got 5 and 1024, because that's a side. Pardon? No, we don't know that the wind is in exactly the east direction. No, east.
W is for
Wind. Yeah, not west. Okay, so I'm doing this pairing right here for sine law, and then I'm doing this pairing for my other piece right here so that I can find theta. Cool? Okay, so you should get 63.3 degrees here. That's actually the measurement of this entire thing. So if I just erase in here so we can see. I know this little piece is 40, and I know this whole thing now is 63.3. So if I wanted to show this in quadrant bearing, south something east, how could I say that? Mark? Okay, so I would want this little red slice inside here, and I would want to be saying south toward the east. And I know if this little slice here that we found in the green is 40, and the whole thing is 63, then I should be able to just subtract 63.3 from 40, which gives me 23.3 degrees. And I can say south 23.3 degrees east. So okay, and that would be our final answer there. Good? Make sense? Just want to make sure this makes sense, because this looks more like an obtuse angle to me.
Yeah, that's what I was, because if you find the other angle, it's 100 and something. Which makes no sense because it's smaller than the...
So, yeah. Little extra thing here before we decide definitively on this is we need to account for the other possibility for theta. When I do sine inverse of a positive, I can have the answer in quadrant 1, which is 63.3, or I can have the answer in quadrant 2. So what's my other option for theta?
116.689.
Yeah,
How did you do that?
we do 180 minus the reference angle. So this is the really, really important thing that we need to remember to do with sine. What did you get, Eden? 116.68, so 7? About? Oops. Okay, so that's actually the entire measurement of this guy. I think we can actually even see if our drawing is like somewhat to scale, even a little bit, we should be able to see that this actually is an obtuse angle. I think that makes sense that this is the proper option. So we need to be really careful when we use sine law for that reason. So if now I take away 40 from 116.7 to get my red slice in here, that should actually make a little bit more sense. So if I do 116.7 minus 40, I'm going to get 76.7 degrees. And that should actually be our direction. You're using, the angle is 116.7. Well, we can see, like, even from our diagram, I know my diagram's not perfect, but I think if we do our diagram, like, relatively well, we can see that this is an obtuse angle and not an acute angle. So we want the obtuse option. Well, if you use, anytime you do the sine inverse of a positive, of course we know we have the two answers. I think if we go to use 63.3, that means that our third angle is 11 degrees. I honestly think that there's no way that you can prove definitively, but if your diagram is even like relatively correct, you can see that it's incorrect. Yep. I don't, yeah, you can use cosine law here. Did you guys get 116.7 using cosine law? Yeah, we could use cosine law. So I wonder if we use cosine law here. Where's my calculator? Let me just plug it in really quickly. So we would want minus 2,4 squared. Oops.
No.
No. Yeah, so if we use cosine law, we get 116.7. So Lewis, a good test that you can do is you can also check with cosine law, because we have all three sides. So if you use cosine law, it actually gives you 116.7 for that angle. So maybe we should just go that route if we have all three sides. Okay. Any questions before we move forward? Okay, so you guys are going to try these last two exercises. I'll give you a couple minutes to kind of get a head start with them. And then you guys we'll kind of take them up as we go here. So see if you guys can figure this one out. This is kind of similar to our video projector. Yep, Mark?
Like, so how do you know when it's ambiguous?
So just to help you guys out with the picture a little bit, if you're developing your picture still, we have a horizontal, and our two ropes have individual tensions, and the ropes are making angles of 50 and 60 with the branch. So you can see that I've labeled that in here. I've also called we'll label one tension number 1 and tension number 2. And we also have a force of gravity acting on our object as well. Okay? One thing that I do know is, just as a little tip for you guys, when I arrange these two tensions tip to tail, so if I take these kind of like out of our scenario and I talk about the tensions themselves, the tensions must be counteracting the force of gravity. So if you figure out the force of gravity, that's kind of like the resultant vector of your tension 1 and your tension 2. Okay? So because these are at equilibrium, the tensions must be counteracting the force of gravity. So yes, the force of gravity acts down, but the tensions must be, the vertical resultant of those tensions must be counteracting the force of gravity. Vanessa?
I have a question.
Yep.
So for like on a test or something, would it be possible for you to like provide the picture and then we like fill everything else in?
That's probably not going to happen. You guys will have to practice with this stuff for sure.
All the time, like I would have a question, like I know what to do, but I don't know like.
If you need clarity, like if you're like, I'm not sure if this 50 goes here or here, you can always ask and I'll decide if I want to tell you. But part of this is like practicing the questions to get to know like where to place the things. Okay? So we do know one thing. We do know a couple things. If we pencil in some horizontals here, I know that tension 2 is actually the same angle to the horizontal here, so this must be 50. I also like to just pencil in another guy right here. So what do I know about this angle? This is a Z pattern right here. Olivia?
How did you get the red drawing? Like you,
So if we're at equilibrium, the tensions must be counteracting the force of gravity. So if I'm arranging the tensions tip to tail, the force of gravity must be that the opposite to the force of gravity must be the vertical force that's counteracting the force of gravity going down here.
and that X is where you put the box.
Yeah, we were doing
We're still doing
X1
No. This is the box here, but I'm just showing, this is the vector diagram over here that shows how the tensions are counteracting the force of gravity.
TX? No, TY is not quite 1.
T1, I found T1.
Okay, so can somebody tell me, looking at this Z pattern right here, what is
50.
this interior angle? This is also 50, okay? What is this angle right here? What's the angle of tension 1 to the horizontal? Let's look over here. That angle should be the same as this angle, agreed?
But that's okay.
So this is the same, right? This is the horizontal, and this is that tension vector. So what's this? 60.
Yeah, but that's not sine law. No, I'm
Yep.
saying whenever we have sine law, the angle's always going to be
Could
positive.
I solve for the third?
I just realized that. You're never going to have a negative angle.
So you can use a variety of Z patterns to probably find some of those angles, right? So I can also use, like if I know this is 50, I know this guy's 40, and I have another Z pattern in here. Because the force of, this force is a vertical force right here. So,
First, the one, like the very first one.
yep, so the vectors tail to tail, you can solve for that. I don't know if it's gonna like help you a lot in this new diagram, but you can.
G's not 21.
Yeah, no, it's okay.
No, because you split it off into a right angle triangle, because you split the two, right in half, right where FG is.
But then
And
you won't
then-
have any.
No, because it's not split in half.
Equally.
It's not split in half.
You don't know if it's perfectly
Yeah,
split in half.
yeah, it's actually.
These
You have
sides
to
will
use side
not.
law.
These sides will
No,
not be
it's
the
in the
same,
middle.
right? Because they're not the same.
No, that's right.
Yeah.
But
Literally
13.0.
Let me just resume my video. Okay, I'm gonna simplify for you guys what we kind of just figured out in here. We figured out that the two tensions tension 1 and tension 2, they must counteract the force of gravity if this is at equilibrium. Okay, so this is the opposite vector that's counteracting the force of gravity. We found this to be 9.8 newtons by doing mass times acceleration due to gravity. Yes?
Is T1 6.7 newtons?
Yes, it is. Okay, now I know just based on using like Z patterns and my information, guys, let's focus in here, please. I know using my Z patterns and my information about the 50 and 60 angles, we figured out that this is 110 inside here. And then I also used a couple other Z patterns here. I used this Z pattern right here to figure out that this interior angle was 40. And then I subtracted 150 from 180 to find this remaining angle in here. So if I have all angles here and I have one side, I should be able to use sine law and cosine law to solve for any remaining things in here. So let's start with tension 1. Zainab?
How did you find the angles 40 and 30 on the second?
So if I know that, looking over here, if I know that this is 90, do you understand where I got 50 from?
Yeah, you just minus 90 plus the action.
Okay, so I'm using, I'll do it in red for you. I'm using a Z pattern right here. So if I know that this up here is 50 degrees, I know that this tension vector, this tension number 2, must be meeting at the horizontal at 50 degrees right here, which means that this interior angle right here is also 50 degrees. I also know that this is 90 right here. So I know that that extra little piece right there must be 40 degrees. So using a Z pattern here, I know that this angle must be equal to this angle right here, which is 40 and 40. Okay, so lots of Z patterns happening here. And then I get the remaining 30 by just doing 180 minus 110 and 40. Cool? Okay. This requires some practice, and I always love to just like draw these little quadrants at all my corners, just because I know, that way I know where the 90s are and where some parallel lines are to use my Z patterns. Okay? So I'm going to solve this for you really quickly, and then this exercise, I'll also hand out a worksheet to you, but the last exercise will kind of be like your homework exercise. Pardon? Solutions are up, yep. So tension 1.
No, they're probably not going to be. Wouldn't they both have to be equal?
They just both have to equal.
Okay guys, if I want to solve for tension 1, I'm going to solve this expression here. And if I want to solve for tension 2, just so that I don't keep you super long here, I will do this. And I should be able to solve for those relatively easy by just multiplying these sign expressions up, and then I should get my tensions. So I'll let you guys figure that out from home. Final answer, and then you guys are going to try to figure out your directions. We'll pick this up tomorrow. Okay?